Hello everyone. Thank you for attending today's webinar where we will cover object detection and image classification algorithms. My name is Chaitanya Hazare and I'm a part of the AI/ML Solutions Architect team at AWS. I'll be answering your questions today and I'll be your co-host as well. We have a big group on call, so all lines are muted and you can ask your questions at the bottom of the right navigation pane. Our presenter today is Dylan Tong. Dylan has been with AWS for a little bit more than 2.5 years and recently moved over to the AI/ML Partner Solutions Architect team after spending time on the enterprise team. So with that, I'll hand it over to Dylan. Dylan, go for it.
Thanks, Chaitanya. Hi, everyone, partners and friends. I'm Dylan Tong, Partner Solutions Architect and Machine Learning Specialist at AWS. So today's partner exclusive webinar is on image classification object detection algorithms. Because our audience has varying backgrounds, I like to level set on use cases and what I believe is baseline around theory. And while this might not be new to you, so I appreciate your patience. I plan to spend the bulk of the time on applied machine learning, specifically on effective ML on AWS. How do you effectively use, implement, and deploy image classification and object detection solutions on AWS? This is my first webinar on this particular channel, so let me know if you think this is the right direction, and I'll adjust accordingly in the future. So what is image classification? Now, some of you may know of the notorious hot dog app from HBO's TV show Silicon Valley. This is an example of image classification in the simplest form. Given an image, it classifies the image as a hot dog or not a hot dog. More practical applications involve more sophisticated models that can classify images across a larger number of categories. Take, for instance, take an example from one of our computer vision services, Rekognition. Right? Rekognition has both image and video moderation capabilities made possible through image classification. So, for instance, Rekognition classifies images here on the left-hand side as non-sensitive, while images on the right are. However, it classifies them into various forms of sensitivity. The top image is categorized as suggestive with high confidence. It provides a reason. It's because it's a female with swimwear or underwear. And on the bottom right, the image is also properly categorized as sensitive. However, in this case, it's categorized under violence and correctly identifies the presence of weapons. While technically not image classification, image similarity techniques are very similar, no pun intended. Image similarity techniques typically use the same or similar underlying model. The main difference is that these models produce similarity scores between images. The model takes images as inputs, outputs vectors instead of a single predicted class, and uses these vectors to calculate similarity between images, most commonly by measuring the Euclidean distance. The image on the left illustrates Rekognition's facial comparison capabilities. It detects which images are the same person, which are not, and it leverages state-of-the-art models used also for image classification problems, alongside other algorithms like KNN to produce an index to enable similarity search. The image on the right is from a demo app that I created as part of an AWS blog, and it demonstrates how to leverage PyTorch and SageMaker to measure similarity and style within the Zappos.com product catalog. And it demonstrates how to train a Siamese network to accomplish this task. Object detection builds on image classification techniques. It additionally provides object localization by predicting bounding boxes that enclose the objects within an image. So here's a screenshot, again, from the Rekognition demo, which you can run from the AWS console. The object scene detection capabilities in Rekognition is an example of object detection in action. Rekognition detects the various objects, including the people, the cars and skateboards. Given an image, the underlying model returns a bounding box coordinates that if it exceeds the confidence threshold, along with a class prediction of the objects associated with the bounding box. Object detection has been successfully applied to businesses across various industries. For example, one of our customers, John Deere, has smart tractors that leverage object detection capabilities to differentiate weeds from crops and has helped their customers reduce herbicide usage by 90%. And you wouldn't have guessed, Chick-fil-A also leverages object detection and tracking algorithms to ensure their customers are served the freshest waffle fries. While today's webinar is focused on image classification, object detection, I think it's equally important to identify what isn't image classification and object detection problems. And in those cases, you should know that there are other computer vision algorithms available to you. In some use cases, you may desire greater granularity. The picture on the left-hand side here demonstrates semantic segmentation. Think of semantic segmentation as a granular form of image classification. Image classification assigns the entire image to a class, while semantic segmentation classifies each pixel in an image to a class. So for instance, in this case, we have pixels classified as a car, road, person, building, or sidewalk. The image on the right illustrates the concept of instance segmentation. The algorithm is instance aware, meaning the algorithm, for example, can identify each person in the image as a different entity, and it classifies each instance at the pixel level. So you may ask, hey, why would we use object detection if we have these more sophisticated algorithms? There's always a trade-off. Harder problems typically require more computations, and in some cases, you might need to support higher FPS. Object detection algorithms are capable of this. Some cases, maybe the bounding box is preferred because the background is relevant. So there's always a place for all these algorithms, depending on what you're trying to build and the problems you're trying to solve. Here's an example of one of our partners who applied semantic segmentation to geoscience. They segmented rock fragments for quality assessment and fault risks. And on the right, they segmented veins to assess precious metal mining opportunities. And then there's also the concept of landmark detection. So here's another screenshot from Recognition's demonstrating the Recognition's facial analysis capabilities. As you can see here, it also leverages object detection capabilities to detect the head of the person in the picture. However, you can see it also detects key points on the face, such as nose. So landmark detection is a building block that facilitates things like facial and pose and emotion recognition. And landmark detection models predicts points on an image, right? So it's different from object detection, which predicts bounding boxes. Similar to landmark is pose estimation. Pose estimations takes things one step further by predicting the human figures in images. And there are techniques for both 2D and 3D. And these algorithms have been applied to things like sports performance analytics and gesture-driven interfaces. Another algorithm that could be, again, used in conjunction with object detection or image classification in an application. Computer vision is a very broad subject area, a lot of areas under research, and one of these areas is the concept of object tracking. So object detection algorithms are stateless by nature. So for instance, object detection alone cannot associate the identity of the players in the video across the frames. Object tracking algorithms are needed for this. For awareness, just for your awareness, Amazon Recognition Video does provide this capability. Sometimes tracking requires also tackling the problem of re-identification. So for instance, the video on the right here demonstrates the Amazon Go store. So in order to perform object tracking in the store, there's many smart cameras throughout the store, and therefore there's also the challenge of re-identifying people across multiple video feeds. So object detection is a key building block in solving these challenges, but be aware that these type of solutions go beyond the basic object detection algorithms that we discussed today. And in some cases, there's also 3D object detection and tracking might be needed. There's organizations applying various strategies in the realm of things like autonomous driving. In some cases, 3D data is collected from sensors like LiDAR or through the triangulation of camera feeds, and variants of object detection algorithms are needed to operate on 3D data. And today we focus on 2D. All right, so hopefully we're on the same page and what is image classification and object detection, what they are not, and how we should apply these algorithms. So let's level set on some of the mechanics. The computer vision capabilities in AWS leverage modern deep learning techniques, and that will be the focus today. The good news is modern techniques are not only more effective, but they are also much simpler to implement than traditional ones. New and old practitioners of computer vision can easily adopt these algorithms. New techniques simplify the traditional computer vision pipeline by removing the manual feature engineering process and the necessity of domain expertise. So when you look at a modern day computer vision, there's basically heavy use of something called deep convolutional networks that enable end-to-end learning. So features are actually extracted and selected as part of the model training process instead of being a manual process done by the data scientists. Research papers like the one I've linked on the slide provide some insight into what goes on within a CNN. So intuitively, we can see that the early layers extract simple features, for instance, in the form of edge detectors. And then as we go deeper, more sophisticated features are learned. And there's also a larger receptive field. Generally speaking, higher performing architectures are deeper, meaning they have more layers. And essentially these models can learn a more sophisticated representation with more data and ultimately to achieve a higher prediction accuracy. So top performing architectures, just so you know, typically also have unique attributes. For instance, the one that you see here is a diagram of ResNet. This architecture outperforms humans on image classification on the ImageNet database, and it leverages the concept of skip connections to mitigate the problem of vanishing gradients, which is a problem that arises when you're training deep networks. Now, one thing that is constant in modern models is the use of convolutional networks, neural networks. So let's just level set a little bit on the concept here. This slide illustrates another deep CNN, convolutional neural network architecture called VGGNet. The difference between CNNs and ordinary neural networks are the convolutional layers. So the animation here on the left illustrates how convolutional layers work. So as you can see, the convolutions essentially reduce the number, part of the outcomes is it reduces the number of parameters through parameter sharing, and in turn, this enables deeper networks. The final layers of this architecture are fully connected, and that represents what is typical of a classic neural network. As you can see, the fully connected nature of the design doesn't scale well, and it's a limiting problem, especially in computer vision, due to the large inputs required by image data. So note that there's also typically pooling layers, and they're essentially performing up and down sampling. Right, so training, let's talk a little bit about the training and mechanics. Overall, they're pretty simple. The training set consists of, for image classification, the training set consists of images, and the images are input it into the image in the form of tensors. So these are floating per point values per pixel, and the tensors, there's a dimension for each channel, right? Typically 3 for the RGB channels, and each image is labeled with a class ID. That's the ground truth. And typically there's a 4th dimension for the mini batch, and the order typically varies depending on the framework that you use. Most commonly, the final activation is softmax, and the network is ultimately trained to typically minimize a cross entropy. So lastly, making use of, lastly, you can also, a common technique is the use of something called transfer learning, where you can reduce the training time and amount of data required to produce good results. There's a lot of, for example, there's a lot of public model zoos out there that provide pre-trained models. So it turns out that these, by using these pre-trained models, the pre-trained weights have transferable knowledge. So what you can do is these models that have been trained on databases like ImageNet, Coco, and Block, for example, you can leverage transfer learning by selecting a few of the final layers and fine-tuning them on a target data set, and often you can quickly achieve your desired results. Inference simply involves a forward pass on a network with the same inputs, so very simple. Now, object detection algorithms are more sophisticated. Unfortunately, we don't have nearly enough time to describe the mechanics of the algorithms. The internal mechanics of, there's actually many object detection algorithms, and the mechanics of, for example, single shot detection, YOLO, faster RCNN. These are some of the common ones. They're all notably different. What is common is the input and outputs, and I think those are what really matters for a practitioner. So the training set expects, again, images in the same tensor format as described previously. The difference is that ground truth labels need to also consist of bounding box coordinates for each of the objects you want to detect, and you also need to then associate that box with an associated class ID. So note that the bounding box format does vary between frameworks and implementation. Also, training typically involves maximizing MAP, mean average precision. Essentially, that's the precision on the amount of overlap between predicted boxes and the ground truth labels. This slide also provides a link to the YOLO algorithm paper. So if you'd like to learn the details, there's a lot of public resources. At the high level, what YOLO does is it breaks down the image into grids, and it does a forward pass. It's performed on each of the grids to predict the bounding boxes for each of the classes that you're trying to train on, and then predictions are made. Bounding boxes are then suppressed based on a threshold to produce a final prediction. Okay, so let's see here. Okay, I'm missing something. So on the inference side, again, it's just simply a forward pass to the network, and very simple. So let's spend a little time now and talk about how we build and deploy these algorithms effectively on AWS. So what you see here is the AWS stack. You may have seen this before, probably new to some other folks, so I'm just going to quickly talk about this. The bottom layer, we have the infrastructure services. So we have things like P3 EC2 instances that are optimized for deep learning workloads. They're packed with NVIDIA's latest V100 GPUs. And we have ways to simplify deployment of frameworks and libraries through a deep learning AMI. Partners and customers sometimes start at this layer because they may have well-established processes and systems for machine learning, and where they want to simply start off with in the cloud is just lift and shift and just gaining the core benefits of the cloud. Eventually, and some other partners will then start moving up stack to the ML services because they realize that they don't really see value in maintaining and building automation for ML ops. So they leverage SageMaker, which facilitates the end-to-end machine learning process. At the very top are the AI services designed to enable developers that might not have experience in machine learning, but want to create intelligent apps. So in some cases, partners look to AI services as a means to quickly go to market. And simultaneously, they will leverage ML services in conjunction to evolve the capabilities and develop more tailored features over the course of the product lifetime. So the services that provide out-of-the-box image classification and object detection capabilities are Rekognition and Amazon SageMaker. And how you use these services, basically leveraging the right strategy, the right services, the right SageMaker capabilities for the problem, for the project, can make a huge difference in the quality, the cost, and the time to market of your image classification and object detection capabilities that you're creating. Rekognition is a fully managed vision API. So generally my recommendation is if you think Rekognition has a chance of addressing your needs, invest a few days, test it out. Either you get a big payoff from a quick win, or you're going to fail fast with little cost and risk. Now, if Rekognition isn't an option, consider using SageMaker algorithms. So SageMaker has a number of built-in algorithms that include image classification, object detection, as well as semantic segmentation. Using SageMaker algorithms will allow you to build, train, and deploy these models with little to no code. Now, if this doesn't work out for you, there are still options, right? It may be possible that you're not able to meet your FPS or resource footprint requirements with Amazon SageMaker's object detection algorithm. Right, that algorithm happens to use something called single shot detection, and it's backed by either a ResNet 50 or a VGG16 network. So if you need to look to an alternative implementation to address your needs, the next fastest route is the bring your own script on SageMaker strategy. So what you can do is you could run your own, for example, TensorFlow or MXNet script for YOLO v3, which could be backed by MobileNet instead. And this script doesn't require any AWS specific dependencies, but you're able to run that on SageMaker, which ultimately then improves productivity and the quality of your delivery through the automation capabilities. And then lastly, finally, in a rare case, that doesn't work for you, perhaps you need to run an algorithm in an environment that isn't among the native frameworks, right? For example, for some reason you want to run YOLO v3 darknet on C, you could package that algorithm in a SageMaker compatible container and still reap some of the automation benefits of SageMaker. Nonetheless, be aware that what you're seeing here in this chart, that there is a trade-off between flexibility and the time to market. Just consider these options in the order that I mentioned. All right, so let's dig a little deeper and understand these options. So first, there's Rekognition, which provides a fully managed vision API. Let's reiterate on some of the image classification object detection capabilities that are available to you out of the box. So one is image and video moderation, object and scene detection, and we didn't mention this previously, but there's also celebrity recognition. So the photo here on the top right, we see Rekognition correctly classifies the image photo as Jeff Bezos and also localizes his face in the picture. There's also people pathing, or AKA tracking, goes beyond basic object detection but it's something that Rekognition provides. It tracks the person, but also maintains a person ID or index within each video frame, along with location and landmarks. Uh, there's also, and as well, there's facial comparison and analysis. So secondly, there's SageMaker. This is the end-to-end machine learning service on AWS. If you need to build your own image classification object detection models, highly advantageous to do so on SageMaker. So let's take a look at some of the components that will help accelerate your computer vision project. So if you're looking to build your own deep learning model and you're planning to tackle some non-trivial problems, let's say you need to model for a large number of classes, you need to be adaptable to unpredictable environments such as varying video and image qualities, unexpected variations in lighting. You need to deal with data sets that are constantly changing, for instance, maybe images in a product catalog. You need a solution to manage your training data. So SageMaker has a capability called Ground Truth. It provides workflows out of the box to integrate with labeling workforces. These could be private labelers within your organization, as well as external workforces from Mechanical Turk, as well as partner services available within the AWS Marketplace. It includes capabilities like annotation consolidation to improve label quality, as well as automatic labeling through active learning. So here's a couple of screenshots. So out of the box, there are templates and there's editors that are available for image classification and object detection. So very easy to create your training set. So once you have, once you have your data set and you start training your image classification object detection algorithms, you can do so little or no code, as I mentioned, right? There are partner algorithms that are available in a marketplace, and then there's also algorithms provided by SageMaker, so which includes image classification as well as object detection. So I want to spend a little bit of time providing you some tips. So if you use the image classification algorithm, some helpful things to consider. First, I recommend pre-processing your data into record IO formats. So record IO is an optimized file format for training on MXNet. It's going to reduce your training time and reduce resource consumption. There's a script called im2rec that you should use to assist with the processing. Now, if you don't want to bother with the effort, I think the next big thing is the best thing to do is to at least create an augmented manifest, which describes the location of the data, your data set within S3. Ultimately, this file will allow you to train SageMaker in pipe mode. So instead of file mode, where you copy the entire data set from S3 over to the SageMaker instances, pipe mode streams the data sets directly from S3. So this provides a better means of scaling to large data sets and also reduces the training startup time and overall training performance. Also, I highly recommend to use the P3 instances for training. You're going to get more than a magnitude improvement in training performance compared to CPU. The underlying image classification model leverages a resonant architecture, so there's a lot of parameters, a lot of computations, and GPU training is essential. From a tuning perspective, when you select your configurations and hyperparameters, ensure you use a pre-trained model set to 1. This enables transfer learning and will generally help to reduce training time and help produce better results. Also, I would recommend to select an augmentation type. This enables data augmentation and again will generally improve the quality of your model. The same tips apply for object detection. One minor difference is that data augmentation always happens by default. You also have the choice between using VGG16 or ResNet 50 as a network to use with the single shot detection algorithm. If you only have time to test one, I would go with ResNet 50, which is a smaller footprint and generally achieves better results. All right, so once you configure your algorithm, you can then launch training jobs in SageMaker, and there's zero setup required. You pay for what you use, and particularly helpful for large-scale training where you don't need to worry about setting up a distributed cluster. Another really helpful tool is SageMaker's ability to automate hyperparameter tuning. SageMaker uses something called Bayesian optimization to search for optimal hyperparameters. So what you see here is what you see here is basically a simple visualization of Bayesian optimization action to, for example, find the optimal learning rate to maximize an objective metric like MAP. Ultimately, Bayesian optimization has been demonstrated to be more effective than techniques like random and grid search, and ultimately, it's going to help reduce training time and costs. So once you have a model ready for use, then SageMaker supports both hosted endpoints for real-time inference and also batch transform jobs for transient processing jobs. Since the underlying models are deep CNNs, a GPU is often the better choice for inference. So SageMaker also supports elastic inference for low-cost GPU inference costs. So for those who are unfamiliar, elastic inference provides the ability to attach GPU to any EC2 instance. So here are some performance tests provided by service teams. What we see here are tests run on Inception v3 and ResNet 152. These are both deep CNN architectures. And then on the far right, we have SSD, that stands for single shot detection. That's the object detection algorithm that was aforementioned. As you can see, elastic inference, right, delivers higher throughput than the P2s. Those are the previous generation of our ML optimized instances, and they sport the Tesla K80 GPUs. The P3s, which run on the V100 GPUs, perform much better, but as you can see, at a much higher cost. So take note that the elastic inference does run over the network, so there is a higher latency, but obviously, as you can see here, it provides the benefit of higher throughput at low cost. So if high throughput and low latency is a requirement, then that's the case where you may want to consider using the P3 instances. All right, so let's talk about the case where you want to run an external algorithm. And so let's consider some of the core components that we would want to leverage as part of building an external algorithm. So, most likely, we're going to use a deep learning framework, right? If we plan on implementing a state-of-the-art solution. Optional, but having a higher level interface like Keras or Gluon, I find helps with rapid prototyping. And for those unfamiliar with Gluon, it provides a high level interface for MXNet and very similar to PyTorch. So like PyTorch, it also provides a hybrid interface that supports both imperative and declarative modes, allowing for ease of development and during experimentation, but also high performance in production. We also would likely want to add complementary libraries, likely OpenCV and all these frameworks and libraries are essentially out of the box or available out of the box, either through the deep learning AMI or SageMaker. So what should you use? At the end of the day, it's your choice. I recommend going with what your team is most comfortable with. All these frameworks and libraries environments are supported on AWS, on SageMaker, and Deep Learning AMI. But if you don't have a strong preference, my recommendation is to leverage the stack here that I've highlighted in green. I highly recommend first leveraging SageMaker to accelerate your projects just for the aforementioned reasons. But you may wonder, hey, why Gluon and MXNet? Well, first of all, to be clear, I'm a fan of TensorFlow and PyTorch. These frameworks provide great capabilities. It has an incredible community and they run great on AWS. Nonetheless, I generally recommend partners to use MXNet and Gluon on reason being our ability to develop or our ability to support our partners. So AWS has a dedicated team of engineers and scientists that develop MXNet and Gluon. Secondly, it also has merits. It has merits of an excellent framework. Despite lacking in terms of the level of adoption compared to PyTorch and TensorFlow, there are a number of benchmarks that have demonstrated MXNet's a leader when it comes to the ability to scale efficiently. Furthermore, some notable useful toolkits have been built on Gluon, including something called Gluon CV, a toolkit specialized for computer vision. And as you can see here, there's a lot of capabilities just to support your image classification and object detection algorithms. So among many things is a model zoo that consists of a large number of state-of-the-art computer vision algorithms that have been implemented on MXNet. So this includes algorithms for, as mentioned, algorithms for image classification, object detection, and for researchers, this allows them to perform rapid baselining, and for practitioners, helps them hit the ground running. So why is it useful to have an arsenal of image classification object detection algorithms? Well, really there isn't a one single best algorithm. And it's illustrated in this diagram here. You can actually find it from the Gluon CV site. Well, there's essentially always a trade-off, right, involved. And in terms of these algorithms, typically between accuracy, throughput, and the resource footprint. The object detection algorithm in particular offers a compelling range of choices. So you can see here on one end, on the blue side, right, we have faster RCNN, which delivers clearly the highest accuracy, but at the cost of throughput and as well as resource footprint. YOLO v3 on MobileNet, on the other hand, sacrifices accuracy for lower resource consumption and higher throughput. So one algorithm is critical when accuracy is paramount, and the other one is better suited to deliver high frames per second and running on lightweight edge devices. And you can see YOLO v3, backed by Darknet, offers a good balance. So among other things, there are numerous useful utilities. Particularly useful utilities include things like automatic data augmentation functions, which really reduce the implementation effort involved in achieving state-of-the-art performance. And last but not least, very easy to run on SageMaker. MXNet is a first-class citizen on SageMaker. You can bring your Gluon CV scripts as is, launch SageMaker managed containers for MXNet. The link that I provided here takes you to a notebook which I've created to demonstrate how to run a YOLO v3 algorithm built on Gluon CV on SageMaker. so next I want to spend a moment to discuss some advanced yet relatively common deployment scenarios. Right, so one common and potentially challenging application of image classification and object detection algorithms is designing inference pipelines on large volumes of video streams for analytics. The Kinesis video streams team has helped simplify these solutions by providing a quick start solution. And what you see here is a solution diagram or solution architecture diagram for that. So what you see, in this diagram here, you can see at step one, the Kinesis video stream provides a scalable point to ingest video streams. And then we have a service that's running on ECS Fargate, right? This is our clusterless container service, and it's configured to scale and consume the video stream while managing checkpoints in DynamoDB, and it enriches the stream by performing inference against the SageMaker hosted endpoint, right? So this could be an image classification or an object detection algorithm. The inference results are then relayed or streamed into a Kinesis data stream. And at this point, this is where the solution could be augmented, right? The inference results could be fed into a data lake and other databases for analytics. It could be merged with or remerged with the video stream to create some enriched video feed. So the diagram illustrates it also illustrates enrichment from a single model, but we can generalize this. We can extend it, and the video stream could, for example, fan out to a numerous parallel pipelines, and inference could be made against a variety of models. So overall, a good solution when near real time is appropriate. And what you really need is something that is designed for flexibility and scale. In some other cases, low latency is critical. So actions need to be taken within milliseconds of object detection. Autonomous driving systems that are designed to take reactive safety measures. For instance, running inference at the edge, right, could be a viable solution. There's also related challenges. For instance, if you are running these algorithms like object detection on a factory floor, there could be other limitations in terms of bandwidth, right? A factory is in a remote region. You're limited in terms of ability to stream high volumes of video data. You may also be challenged by regulations. You might require the video streams to remain on site. Some cases, availability is critical, yet the system is deployed in an area with an unreliable network. So there's no reliable connection to the cloud. So these are cases where you may want to do inference at the edge. Object detection algorithms in particular are often run at the edge. So to help manage the complexities of deployment and managing and optimizing models across the cloud and various edge devices, SageMaker has a capability called Neo, which could be leveraged. So the idea is you train your model once, and then you use Neo to recompile the models for edge devices that, for example, run on ARM, like NVIDIA Jetson devices, the Nano, the TX2s, as well as the Raspberry Pi. Cool. All right, so next, as a final part of the webinar, I'd like to go through a demo. And my goal here is I want to give you a sense of the end-to-end process of training and deploying a YOLO v3 model that's built on Gluon CV and SageMaker. So let's get started. All right, so first off, I am going to log into AWS here. I'm already logged in. Okay, but I'll just show you from the very start. So as I log in, if you've never been to SageMaker, just like any other service, just go SageMaker, and that takes us to the console. So the first thing I will probably want to do is create my training set. So this is where I can leverage ground truth. So within ground truth, this is where I can manage various workforces. So there's going to be public workforces, and that's managed out of the box, integrations through, as I mentioned, Mechanical Turk and other labeling vendors from the marketplace. And you can also create a private workforce here, add members in your organization, as well as there's security controls through Cognito. So in the particular project that I created for this demo here, my goal was to, this is one use case that has come up from a few consulting partners, right? They want to be able to detect, QR codes and barcodes of various forms in real time at the edge. So in this demo, the goal here is to be able to deploy and run an object detection algorithm on a Jetson Nano and be able to detect, in this case, these medicine bottles and be able to detect the QR codes. Okay, so I created these ground truth labels. Let me just kind of quickly show you how the interface works. I'm just going to clone one of these labeling jobs. So here, essentially I'm just setting up the location of my raw images. I describe where my labels are going to be outputted. And as you can see here, there's various out-of-the-box templates, right? You can create a custom template, but there's out-of-the-box templates and editors for some common NLP cases, and you can see also for computer vision scenarios. So if we take a look at the bounding box case, let me quickly show you the editor live. Right, I can create a labeling job. This public is for Mechanical Turk. Vendor manages are the marketplace vendors like iMerit. Okay, so let's add a few labels just to show you the editor here. So this is what your labelers will see and what they'll use to create your training set. So for object detection, I get an image, and then very simply, I can just go ahead and create these bounding boxes here. Okay. All right. So once you've gone through this process, now I have this training set. The next thing I want to do is go through a training process, right? I'm likely going to have to do a little bit of experimentation, a little bit of prototyping before I do some large scale training. It's going to be an iterative process. Okay, so the way I'm going to demonstrate this is, unfortunately, I literally actually created this demo or finished creating this demo last night. So the notebook for this demo isn't quite ready. The notebook for the QR codes is not quite ready for demo. So I'm going to actually show you something else. So if you recall previously in the slide, I did mention that I have some other notebooks that would be helpful for demonstrating how to run Gluon CV on SageMaker. So I'm going to use this just to kind of give you a sense of the end-to-end training and deployment process. And this would be a helpful, some helpful resources for you also as a follow-up for this webinar. So I've gone ahead and I've actually cloned this repo over to a SageMaker notebook. So if we just go back to SageMaker here, I'm going to log into that notebook. So the number of managed notebooks you can see of various types. This is the notebook where I've cloned a repo. And let's take a look at this lab here. Different data set, but the same process. So this notebook here actually demonstrates how to train and deploy a YOLO v3 algorithm that was built on Gluon, but it operated on the Caltech birds data set. I'm just going to use this to talk you through the process. So once we've logged, so you can see in the notebook, these are just standard dependencies. Gluon isn't installed on the containers, the training containers, or the hosting containers, as well as the notebooks out of the box. But as long as you have privileges or through lifecycle policies, you can still install Gluon CV on your notebooks. So this is what I've done. So that's the, I've installed Gluon now. And, quite typically you would then bring on your Gluon script, your YOLO script. So I made some modifications to the YOLO script that's available from the Gluon CV site. So you can actually just go to, search for Gluon CV, go over to the site, and there's a YOLO algorithm that you can actually use out of the box. And you probably want to make just some minor changes to the script. You can see here that there needs to be a method, like there's no SageMaker specific dependencies in the script, but you do need a way for passing parameters, like the hyperparameters and different options to the script. So I did have to add some code to do that. And quite often, it's just handy in the early stages to just be able to run the scripts on the notebook. So you can deploy a notebook on the P3 instances, for example, and do GPU training on these notebook instances. And that's actually what I typically do for these computer vision projects, just to do some rapid prototyping. Essentially what you see here is, like, again, as I mentioned, Gluon CV isn't installed by default on any of the SageMaker net managed containers, but that's not a problem. What SageMaker team, the SageMaker team does manage MXNet training and hosting containers. And all we really need to do is install dependencies, the Gluon CV dependencies on those containers through using a requirements.txt file. And that would address the problem and avoid the whole need of needing to build and manage my own container. So what you see here is just setting some of those dependencies, kind of preparing for deploying a training job, and then I'm setting some hyperparameters. And one of the things that you can do in SageMaker is called local mode. So yes, you can run your script just locally as is, but sometimes you actually want to deploy the container actually locally on a notebook just to just to test the deployment process before you do it remotely. So this kind of illustrates that process. So before I deploy the training job remotely, I'm just going to run the test and just make sure that I can actually deploy my script successfully into the MXNet container. And what makes it local is that I just set this parameter here, the training instance type is local. So once I do that, I find that my script successfully deploys locally. I'm confident that when I then deploy it remotely, that the process will succeed. So I'm then good to go. And what I would typically do next as a starting point is to launch a hyperparameter tuning job, right? So as I mentioned, this is the hyperparameter tuning jobs leverage Bayesian optimization to search for optimal hyperparameters on my behalf. So by launching a hyperparameter tuning job, I would, for object detection, I'm trying to maximize on map. And then I can essentially define, so I'm just going back up here. And so I'm maximizing map, and then I can define the different ranges that I want to search on. So for example, I want to explore the different optimizers, atoms, stochastic gradient descent, the learning rate, and the batch size. These are typically the the hyperparameters that have the greatest influence. So, as a tip, both image classification and object detection, these are the hyperparameters that you want to perform a hyperparameter search on. So the output of the hyperparameter job will be then a best model. It's going to run a whole bunch of jobs. It's going to explore a whole bunch of different hyperparameters which you've selected to search on. In my case, again, learning rate, the optimizer, and batch size. Once I have a sense of optimal hyperparameters and I have a partially trained model, then I might want to then start kind of nursing the model, that one model along. So I can take that model artifact and I have the ability to then do incremental training. So here's an example of, now I'm deploying a training job and I'm taking the model artifacts, for example, that were produced by the hyperparameter tuning process. And then I'm now handpicking some hyperparameters and I'm just kind of doing incremental training on that one model, using essentially this as a checkpoint. Right. So this is kind of the process that would take. Eventually, I'm going to get a model that I'm happy with. It meets the business requirements. I want to then host it. So I could then deploy a batch transform job, or in this case, I'm going to deploy a real-time endpoint, which is very simple. As you can see here, describe the model, the infrastructure, my model serving script, and then run deploy, right? And now it's good to go. So what I'm showing you here is the SDK interface. You can do the same thing through the console and the CLI. So for instance, let's kind of drop back out here. So you can see here, I can go ahead and also configure my hyperparameter tuning jobs, my training jobs here right from the console. So in fact, if I didn't feel the need to use YOLO, right? If I think SSD is perfectly fine, then I choose the object detection algorithm. I can actually go and build and train my model without writing any code at all. I just come in here and I simply configure these hyperparameters and I launch straight from the console, no code necessary. Cool. All right, so once I've gone through the process, I may have deployed a model, I do some testing. Eventually now I want to then be able to deploy this onto my Jetson Nano. So in this case, I have actually used YOLO v3 on MobileNet. So relatively speaking, it's a pretty compact model. Let's actually take a look at some of the artifacts here. So this is Neo. And let me show you this one right here. So this was a
Hey,
YOLO
Dylan.
v3. Yes.
Hi. We are getting to like the 60-minute mark. Yeah, so just wanted to do a quick time check. Thank you.
Okay, thanks. Yeah, let me just kind of speed along. Okay, so all right, so once I have the hyperparameters, then I can go, next thing I want to do is I want to create an optimized model. So it was very simple. I just come in Neo, again, through the SDK or through the console. I simply create a compilation job. I'll point it to the model artifacts, right? And then, actually, let me clone the job here. Oops. Okay. So I select my model artifacts, and you can see I can specify, in this case, the MXNet framework, and I can choose a target device like the Jetson TX2 and the Nano. Okay, and once I have now I have some artifacts that could run in something called a deep learning runtime and can run on the ARM architecture. So let me log in here. Let me log over to my Nano now. Okay. All right, so the Nano has, just to show you a few things. I think, so it doesn't have, it has, as you can see here, it has doesn't have too much resources, right? So we're definitely on a resource constrained device. And again, here, our goal here now is to create my QR detector. So some of you may be aware that there are some, like OpenCV actually has a QR code detector called ZBar. So let me kind of show you a few things. So if I'm going to run PyZBar, the script here, and you can see it works perfectly fine. This is a high resolution image. It does a great job at detecting these QR codes. The challenge is, though, things like the Nano, they don't have, and let's say, quite often the camera feed is not high quality. So I have this script here. Let me just quickly show you, called QR detect py, and it's using PyZBar, and essentially is using it to detect. Let me just run it right here. Oops. You'll see that unfortunately it will not be able to detect the QR code from the camera. So here I have a bottle, and unfortunately PyZBar isn't able to detect the QR code. It needs a higher resolution image. So what I've done is I've created my own QR model, as I showed previously. So let me show you the models here. So I actually have a couple of models. Just to show you, just want to show you a few things. So I have a symbolic model, and you can see, just take note of the size here, and then we compare it to like the DLR, right? There's actually there's some reduction in size. Okay, and then I also, so now I'm going to go and run this model. I QR detect v2. Let me just show you this really quickly. Okay. So instead of using PyZBar, and this code here is reading from a GStream, and essentially, yeah, it's doing inference on this local endpoint here. Actually, it's easier to see the code from here. Okay. All right. So you can So there's inference on my DLR model, and you can see it's essentially loaded. It's loaded through here. Okay. So I've installed something called the DLR runtime right here. Okay, so now let's run my model. Let's do Python 3 QR detect.
Maybe put it in the back a little bit.
Yes, sir. There's the FPS is really low because I'm actually running
You want to keep it on
X11
something
forward.
stable? Maybe that will
So,
help.
actually, normally it detects it immediately. I think I just have bad luck for some reason. I don't know why it's not working
Well,
right now.
live demos require sacrifice, so you did take a chance. That's an awesome thing to show off. But
There it
we
is.
might,
Yeah.
yeah.
Yeah, it's a little kind of hard. Unfortunately, the FPS is really low because we're running a web conference
Hey,
and
Dylan, so do you want to
I'm doing
summarize
X11
a bit
forward.
now?
Right. So yeah, this is kind of this is the end of the demo. So we've covered a lot. Image classification, object detection. Yeah, this isn't really. I don't consider this the end of the webinar. Both Chaitanya and I are here to work with our partners. Any projects, computer vision. If you need additional, if you want to leverage our experience around image classification, object detection projects, we're here to work with you. I've pointed you to some various resources, and if you're interested in running some of these workshops live, that's something that we can also do if that's of value.
So thanks a lot, Dylan. Do you want to flash your email address once, please, and your name? And there are a lot of requests for the slides content and the notebook contents as well.
Okay, sounds good. That's great. That's frustrating. It was working really well earlier. um, okay,
Ah,
there it is.
yes,
There it is. Yeah, I just need to
success.
this test. Okay, yeah. So let me go
That's a nice
and
way to end it.
yes. So here is my email, and we will share the presentation content with everyone.
Awesome. So thank you very much, Dylan. So everyone, before you sign off completely, we'll ask you just a few questions via survey, which will pop up when you leave the call. Also, you will get an email in about maybe 6 hours from now with the video file for this call. And thank you very much, Dylan, for that awesome presentation and awesome demo. And thanks everyone for joining and for attending our presentation on object detection and image segmentation today. Any closing thoughts, Dylan?
No, I think you did a great job summarizing.
Thank you very much. Bye.
Bye.